In this section, we're going to talk about air infiltration or air leakage and how to seal our building shells for comfort and energy efficiency. Air sealing is one of the biggest opportunities that we so often miss. So air leakage impacts energy consumption. Cold air leaking in the winter increases our heating bills. Hot air leaking in the summer increases our cooling bills. But it also impacts comfort and the indoor air quality, whether it's moisture transmission from the crawl space, particles from the attic or the crawl space, or odor entering our house from those attached spaces. So our tool for measuring air leakage and quantifying it is called a blower door. This device uses a large fan and a nylon skirt to place it in a door, and that large fan exhausts large quantities of air from our house. That large quantity of air exhausted after we close all the doors and the windows equates to the actual amount of air that's able to leak into the house. So if we, for example, can exhaust 2,000 cubic feet per minute of air through our blower door with all the doors and windows closed, that means the leaks in that house equate to 2,000 CFM of air leakage. So we always use a standard test pressure of 50 pascals. A pascal is a metric measurement of pressure and is equal to 2/10 of an inch of water column. We depressurize our house with the blower door fan to 50 pascals and measure the leakage at that pressure. At that pressure, the amount of leakage we measure is typically about 20 times the amount of average or typical leakage that would occur in the house. In this sketch, we show the blower door discharging a bunch of air, blowing air out of the house, and we show that there's several locations through the ceiling, through the rim joist, out of the basement, through interior partition walls, where air leaks back into the house to replace that air that we've exhausted with the blower door. Our goal is to use the blower door to guide us as we seal the air leaks in our house. We want to make constant progress, constant reduction in the leakage amount as we work through our sealing process. So when we view a typical simulation of heat loss from a house, in many climates, the top item on our list is air infiltration. This is a mild climate in the Sacramento-San Joaquin Valley of California, and we see that the number one heat loss is actually air leakage in the model that's used. Number two is windows. Number three for a slab-on-grade house is slab edge insulation heat loss. So we can see that the air infiltration is one of the big three. So this is a slide that came from national research, and it's all housing stocks and where we typically find air leakage. It's so often believed that most of the air leakage is from our doors and windows. We spend a lot of time around our doors and windows and often feel drafts at those locations, so we just kind of assume that that's where the majority of the leakage is. In actuality, the research shows us that only about 21% of the air leakage into and out of a house is at the location of doors and windows. This whole notion that that's where our leaks are has been reinforced, especially right after 9/11, when the government issued an advisory that we should all have plastic and duct tape available at our homes. So we could seal the leaks in our doors and windows with plastic and duct tape in the event of a chemical attack. But again, the research shows that that's only about 21% of the leakage. The other 79% comes from other locations, especially locations like the top plate, the sill plate, where the drywall, the wall drywall, doesn't seal airtight and form a continuous pressure boundary between us and the attic. And all the other locations are here: plumbing penetration, the duct system, electrical. So this is some research that shows the leakage on typical houses. And these are actually typical new houses. And one thing with the performance of all energy features, we see a tremendous range. Our best houses here only leak about 2 air changes per hour at 50 pascals, our standard test pressure. And the worst houses here are almost 10 air changes per hour. So that tremendous variation in actual leakage makes it imperative that when we work on a house, we actually use the blower door to quantify it, so we know whether or not we're in a house that's relatively tight in that 1 to 3 air changes per hour at 50 range, or one that's loose over about 6 air changes per hour at 50 and needs significant air sealing. We also have data on where a house leaks to and from. This is some research from the Southwest where slab-on-grade houses, about 50% of their leakage, shown in blue here, is all from the attic. So that's one of the worst places we want leakage to go to and from, especially in the summer in the Southwest, in that hot air out of the attic leaks down into your house in the summer, greatly increasing the cooling cost of homes in the Southwest. The other 2 categories here, we see about 10% of the leakage is between the house and the garage. Another bad location to have air leak from, in that the air in the garage with car exhaust, stored gasoline, paints, pesticides, and other chemicals, the air in the garage can be quite bad, and we don't want that air leaking into the house. And then all other equates to about 40% through the walls and at the slab edge. So often we think that the new technology, like the new advanced house wraps and weather-resistive barriers, make it easy to decrease air infiltration. But if we're not taking a systematic approach to air sealing, sealing not only the walls, but the junction between the walls and the floor system or the slab, between the walls and the pressure boundary at the ceiling, we don't end up with a tight building. One research effort showed that houses with house wrap compared to houses using just tar paper for the weather-resistive barrier, there was no difference in the air infiltration rates between the 2. So one thing that we have to be cautious of as we air seal buildings is that it can have a negative impact on other building features. So as we air seal or tighten a conventional building, what happens to the combustion safety in that building? As we tighten it up, we make atmospherically vented combustion appliances that are located inside the house potentially more dangerous. They don't have as much free air communication with the outside. So there's more of a competition for air between bathroom exhaust fans, kitchen range exhaust, and that competition may cause an atmospherically vented water heater located inside the house to backdraft, spilling its combustion byproducts inside the house. So as we air seal, we need to, before we begin and after we finish, assure that we haven't negatively impacted combustion safety. The same is true with moisture. Often it's excessive air infiltration that helps carry moisture out of our houses, especially in the wintertime. And carrying that moisture out gets reduced as we air seal, so we may have more issue with moisture problems in the house as we air seal. And of course, indoor air quality. We often rely on air leakage to help us ventilate the air in our house to keep our indoor air better. And as we air seal and reduce that leakage, we have to pay attention to indoor air quality. So as we pursue air sealing, we have to keep in mind the whole house as a system concept and making sure we don't do damage in other areas. One of the first things we do as we air seal is we look for the big holes. In architecturally complex buildings, we see many missing fire stops like this thick wall with an open wall cavity showing at the top. So our hierarchy for sealing leaks, we always want to seal big holes first before little holes. We always want to seal holes that are located either high or low in the building and that the driving force pressures are higher, both high and low in the building. So big leaks, high and low leaks, and always leaks to the attic since our attics are so hot in many climates. So here it shows the typical places in an attic plane where we find leaks. Electrical boxes, plumbing penetrations, the attic access hatch, around a masonry chimney, around an exhaust fan, and the big diffuse leak is where the wall drywall doesn't seal airtight to the double top plates on the interior partition walls. So we're always sealing our ceiling drywall to the top plate 2x4. The very best way to identify air infiltration paths is to use our infrared camera. We slightly depressurize the building using a blower door, exhausting air from the house, and we do that for several minutes when we have at least 15 degrees Fahrenheit temperature difference between inside and outside. Once we run the blower door for 15 minutes, we're able to see the air leaks even if they're inside a wall with our infrared camera. So we get to see two things simultaneously, where the insulation isn't performing, but also where air is leaking into the house. So this is an example of, in the winter, cold air leaking down into an interior partition wall. And we can see all the cold streaks in between the boarded interior partition wall. Here's a newer building. Again, in the winter time, we see the cold air leaking down into this big interior interstitial space, turning it into exterior wall, even though as we glance at it, we think it's completely interior. But because we're missing the fire stop at the top of that wall, it's all open to the attic, greatly increasing air infiltration in that part of the house. And here's a summer air infiltration leak. It's around a simple recessed light fixture where hot air leaks out of the attic and into the fixture. And we see the hot streaks across the ceiling level. This illustrates why it's so important to depressurize the house as we film it in infrared when we look for these leaks. If we hadn't reversed this leak, we wouldn't see much at the recessed light fixture. But as we accentuate it with the blower door, exerting about 20 times more pressure than the building typically sees, then we can see these leaks quite easily. And again, when we provide this feedback from the blower door and the infrared camera, it makes it much easier to find the leaks and much easier to train our workers where to look for the leaks and how to seal them.